This is the 14th lecture of my series on thermodynamics. In the previous lecture, we met the notion of absolute temperature. We saw that if you have a reversible engine running between two reservoirs at temperatures T1 and T2, then the ratio of the heat rejected minus Q minus to the heat taken in Q plus is given by the ratio of the two temperatures in a given scale, the absolute temperature scale. So Q minus R by QR plus works out to be minus T2 by T1, where T2 and T1 are the absolute temperatures of the two reservoirs. And this immediately told us that the efficiency of this reversible engine, the work done by it divided by the heat taken in Q plus, is given by 1 plus Q minus by Q plus, and therefore it is 1 minus T2 by T1. Now what we are going to do today is use this result to actually establish a very important inequality which will work not just for a reversible engine when running between two reservoirs, but for any engine whatsoever. Let me remind you that a general heat engine would basically take heat from many different reservoirs at temperatures T1, T2, T3 and so on, and the amounts of heat it takes in from these reservoirs will be Q1, Q2, Q3, Qn and so on. And of course, some of these heats will be positive, that is, they will really be taken in. Some will be negative, so they will really be heat rejected. But the sum total of all these heats, sum over Qi, and here I put a circle on the sigma just to indicate that this is a cyclic process that's going on, must be equal to the net work done by the process, simply because this being a cycle means the change in internal energy for the system has to be zero. Now, we will see that the heats taken in at different temperatures obeys a very interesting inequality, not really directly the heats, but the ratios of Qs and the temperatures at which they are taken in. Turns out that if you add up the Q divided by the temperature, that is Q1 by T1 to Q2 by T2 to Q3 by T3 and so on, this sum can never be positive. And this is what is called the Clausius inequality. This inequality is what we are going to prove in today's lecture. Now, to prove the Clausius inequality, what we will do is we will start by assuming that in addition to my general heat engine, I have one more reservoir, a reservoir at some absolute temperature of T0. Let's call this reservoir R0. Now, we will play a game which should be pretty familiar to you by now, because we have done this thing over and over again over the last few lectures. We will try to ensure that somehow we take these reservoirs R1, R2, R3, etc. inside my engine, or at least imagine a bigger engine in which R1, R2, R3, etc. are also parts of the engine. But let me remind you that in order to qualify as a working substance of an engine, the substance has to go back to its same state. So that is exactly what we have to do to the reservoirs in order to be able to include them as part of my engine's working substance. So what we will do is we will run a reversible engine, a Carnot engine, C1, between the reservoirs R0 and R1. And basically what I am going to ensure here is by adjusting the scale of this Carnot cycle C1, I am going to end up with a situation where Q1, the heat rejected by R1 onto E, that is heat given by R1 to E, and Q minus 1, the heat which is actually given by R1 to C1, add up to 0. In other words, the amount of heat R1 rejects to the substance here is actually given back by this Carnot cycle, so that R1 returns back to its same state. And we will not stop, of course, at doing this to R1. We will also do it to all of these reservoirs. That is, between every one of the reservoirs, including these ones which we have not drawn, we will run a Carnot engine. For example, between the nth reservoir Rn at temperature Tn and the one single reservoir R0, this extra reservoir that I am talking about here, I will run a Carnot cycle Cn, and all these Carnot cycles will essentially do one thing and one thing only. Each one of them will give back to the corresponding reservoir R1, R2, R3, or whichever reservoir is connected to, exactly the same amount of heat that the reservoir gave to the system. In other words, we will have to ensure that Q1 minus the heat taken from R1 by C1 and Q1, the heat taken from R1 by the engine, add up to 0. Similarly, Q2 minus and Q2 add up to 0, and so on. In general, Qn minus and Qn will add up to 0. All of these will have to add up to 0. Now, as a result of all this, what will happen is that the engine, of course, has gone in a cycle. The working substance of the engine is back to its initial state. But not only that, the reservoir R1 has received back exactly the amount of heat that given. The same for R2, the same for R3, same for each and every one of the reservoirs. So we can put all of these reservoirs as parts of the working substance of a bigger engine. Not only that, all these Carnot cycles that we are using here, these are also all reversible cycles. So the working substance of each of these have also gone back to their original state. So at the end of the day, we can include each and every one of these, the original engine, all these reservoirs, and all these Carnot cycles as part of a big super engine. Now, this super engine, of course, we can sort of denote by a dashed line like this. Everything inside this is part of my super engine. Now, what is this super engine doing? Different parts of this engine are doing work. For example, the engine itself is doing work W, and then all these Carnot engines do their own work. But what is very important for us is that each one of these engines ultimately take heat from one reservoir and one reservoir only. And that is the heat which is taken in by each of these Carnot engines from the reservoir R0. So basically, the net heat taken in by this engine from this single reservoir R0 is given by Q1 plus Q2 plus Q3 plus and so on, right up to Qn plus for all the n's. Now, note that we have this result already, that for a Carnot cycle running between two reservoirs at temperature Tn and temperature T0, Qn minus by Qn plus is minus Tn by T0. This is the result which helped us to establish the absolute temperature scale in the last lecture. So Qn plus is simply minus T0 times Qn minus by Tn, but Qn minus, remember, is nothing but minus Qn. Note that the net amount of heat given out by this reservoir is 0, so Qn plus Qn minus is 0. And therefore, Qn plus, the heat taken in from the reservoir R0 by this particular Carnot cycle Cn is given by T0 into Qn by Tn. So now that we consider all of these together to be my super cycle, the net heat which it takes in is simply the sum of all these Qn pluses, and that heat Q0 is simply sum of all these Qn pluses, and therefore is T0 times sum of Qn by Tn, where the sum, of course, is over all of these reservoirs. That means it's over the entire cycle. And because this is a cyclic sum, you have put a circle on the sigma sign, just to indicate that. Now note that the upshot of all this is that we have this big cycle which interacts with only one reservoir at temperature T0 and draws this much amount of heat. Now, if this heat were positive, then the super engine will draw a positive amount of heat from a single reservoir and convert this completely into work. Of course, it has to convert whatever heat it takes in completely into work, simply because delta U for the entire system, not only our original engine, but all the reservoirs taken together, all the Carnot cycles taken together, is of course 0. Now, if Q0 is 0, this would violate the Kelvin-Planck statement of the second law, because this is exactly what the Kelvin-Planck statement forbids. You cannot have a cyclic process which takes heat from a single reservoir and converts that entirely into a positive amount of work. However, this super engine is something which we can always construct. After all, any engine that we have would be taking heat from a bunch of reservoirs, and we can at least in principle run Carnot cycles between a single reservoir at temperature T0 and all of these reservoirs and end up with a super engine. But right now we figured out that if our Q0, the net heat taken in from R0, were positive, we would be violating the second law of thermodynamics. Of course, we are not allowed to do that. And therefore, our conclusion would be that this super engine cannot draw a positive amount of heat from R0. In other words, Q0, the heat it draws, must be less than or equal to 0. And since Q0 is T0 times this sum, and T0 is a positive number, we end up with this very important inequality. The sum over Qn by Tn for any cyclic process whatsoever, again, the circle here signifies that we are talking of a cyclic process, must be less than or equal to 0. This is the famous Clausius inequality. Now, if our original engine had been a reversible one, then the super engine of ours, made of basically that original engine, all these reservoirs which are back to their same original state, and a bunch of Carnot engines, would also be reversible, simply because the only thing which could have been non-reversible in this whole thing was the engine itself. In that case, of course, you should be able to run the engine both in the forward direction and in the reverse direction. And if you were to run it in reverse direction, all the Qns will become minus Qn. The temperatures, of course, will stay the same. So for the forward process, you would have this inequality, sum over all the reservoirs, Qn by Tn is less than or equal to 0. But at the same time, you would also have, for the reverse process, which is also a possible process, sum over all the reservoirs of minus Qn by Tn is also less than or equal to 0. Now, both of these can be true at the same time only if this sum happens to be 0. So, for a reversible cycle, we have this special result that Qn by Tn added up over the entire cycle must give you 0. Now, in this derivation, we have assumed that the temperature changes discretely during the process, so you have a bunch of discrete reservoirs. But of course, as we have already discussed earlier, if a temperature changes continuously during the process, then we would have to actually imagine an infinite sequence of reservoirs with continuously changing temperatures. In that case, of course, the sum would actually get replaced equivalently by an integral. So for a general continuously changing temperature process, the cyclic integral of d cross q by t carried out over this entire cycle, of course, takes the place of the sum of q by t over the entire cycle, and this is going to be less than or equal to 0. This is the continuous version of the Clausius inequality. And specifically for a reversible process, we will end up with the continuous integral of d cross q reversible by t over any loop that is over any cyclic process, must be 0. Now this integral over a loop must be 0 should remind you of something very special as far as this integrand is concerned. And that is exactly what is going to give us the notion of entropy. But before we go and talk about entropy, let us take a deeper look at the Clausius inequality itself. Now the proof that we have given above of the Clausius inequality is basically something which follows from the second law. We directly use the Kelvin-Planck statement of the second law to actually finally establish the inequality. But even in the steps before that, we use the fact that the heat exchange ratios for a reversible cycle running between two reservoirs is given by the ratio of their absolute temperatures. That in itself was also a consequence of the second law. So the Clausius inequality, of course, is a consequence of the second law. However, as we are going to show right now, it's really equivalent to the second law. That is, all the statements of the second law that we have seen so far can also be obtained as consequences of the Clausius inequality. In other words, the Clausius inequality is yet another version of the second law. To see that, let's first take a look at a situation where you have an engine going in a cycle and interacting with only one reservoir. Because here, because there is only one reservoir, there is only one Q and only one T. So the cyclic integral of Qn by Tn simply becomes Q by T. According to the Clausius inequality, this has to be less than or equal to 0. And since absolute temperature is positive, this implies that Q has to be less than or equal to 0. So if you have an engine which interacts with only one reservoir, the only thing that is possible for the engine to do is to take a negative amount of heat from that reservoir. In other words, it's possible for that engine to convert work, a negative amount of work, that is work done on the system, completely into heat, rejected to the reservoir. But it is impossible for it to take a positive amount of heat from the reservoir and convert that completely into work. This is nothing but the Kelvin-Planck statement of the second law. Since the two statements of the second law that we have seen so far, the Kelvin-Planck and the Clausius statement, are equivalent to each other, it's obvious that now that you have seen that the Clausius inequality can imply the Kelvin-Planck statement, it should also imply the Clausius statement. However, let us just try to see that directly. Suppose you have a two-reservoir engine, as we have in the Clausius statement of the second law, which has no work source or sink, no possibility of doing work. Now that there are two reservoirs at temperatures T1, T2, the Clausius inequality takes the form Q1 by T1 plus Q2 by T2 is less than or equal to 0. However, the fact that there is no work source or sink adds to this the statement that Q1 plus Q2 has to be equal to 0. This is the net heat taken in by the engine, and since delta U is 0 and W is 0, this total Q has to be 0. Since Q2 therefore is minus Q1, the inequality simply becomes Q1 into 1 by T1 minus 1 by T2 is less than or equal to 0. This is the inequality any such two-reservoir engine without a work source or sink would have to obey. Now, among the two temperatures, let's consider T1 to be bigger than T2. If that is the case, then 1 by T1 is smaller than 1 by T2. So therefore, this factor 1 by T1 minus 1 by T2 has to be less than 0. And dividing through by a negative number changes the sign of the inequality. So therefore, this then translates to Q1 must be greater than or equal to 0. So what the Clausius inequality tells us is that for a two-reservoir engine with no work source or sink, heat can only be taken in. Heat can only be positive if the corresponding temperature is higher. It is possible to take heat at a higher temperature and transfer the heat to a lower temperature. But it is not possible to do it the other way around. Q1 cannot be negative or in other words, Q2 cannot be positive here. And that is nothing but the Clausius statement of the second law. Okay, now that we have seen that the Clausius inequality actually gives us the basic statements of the second law, the ones we started out our journey of the second law with, it should not really come as a surprise that the consequences of these statements that we have derived so far, like the Carnot theorems, can also be seen as simple consequences of this inequality. Let us just see that by considering a two-reservoir heat engine. The two heats taken in are Q plus and Q minus at temperatures T1 and T2, and of course, the inequality again takes the form Q plus by T1 plus Q minus by T2 less than equal to 0. But now you note that Q plus plus Q minus has to be equal to W. And therefore, the Q minus here is actually W minus Q plus. So you can just plug that in. And this is the inequality that every heat engine running between two reservoirs must obey. You multiply through by the positive number T2, that keeps the inequality intact. That gives us W plus Q plus into 1 minus T2 by T1 with the minus sign is less than equal to 0. And therefore, just rearranging the whole thing, remember Q plus is a positive quantity, so dividing by that does not change the inequality. So move this to the other side, divide by Q plus, you get W by Q plus has to be less than or equal to 1 minus T2 by T1. W by Q plus is nothing but the efficiency of an engine which runs between these two reservoirs. So efficiency eta works out to less than or equal to 1 minus T2 by T1. Of course, if the engine is reversible, then the inequality in Clausius inequality becomes an equality. So for a reversible engine, the efficiency eta R has to be exactly equal to 1 minus T2 by T1. This essentially is what Carnot's theorems told us. All reversible engines have the same efficiency as long as they are running between the same two reservoirs, and an irreversible engine has to have a lower efficiency. Indeed, using the Clausius inequality, we can prove a much stronger result. We have already seen that Carnot cycles are special because they are the only reversible cycles which are running between two reservoirs, and any engine running between the same two reservoirs cannot be more efficient than a Carnot engine. But that is a statement about engines running between two reservoirs. What about a more general engine? Now, in the case of a more general engine, there will be multiple reservoirs which the engine will interact with. However, if we take the hottest of these reservoirs and the coldest one of them and run a Carnot cycle between these two extreme temperature reservoirs, the efficiency of the Carnot cycle will give us an upper bound on all possible efficiency of this engine. And this is exactly what is called the Generalized Carnot theorem. In order to prove this, let us just denote the largest temperature reached by the substance of the cycle during the whole cycle be T plus. This is the hottest of all the reservoirs available, and let T minus be the smallest of all the temperatures of the reservoirs. Then, Clausius inequality once again tells us that the cyclic sum of Qi by Ti will be less than or equal to 0, and this sum can be split into two pieces. The first part is for all the Qj's which are positive of Qj by Tj, and another for all the Qk's which are negative of Qk by Tk. So this is nothing but the sum here written out with the positive and negative pieces separately. Now, each piece in this sum is positive, and if you were to replace the denominator Tj by a larger value or something which is at least as big, what will happen is this side will become even smaller. So replacing all the Tj's here by T plus will change this to something which is even smaller. On the other hand, all these terms here are negative. So if you were to replace all the TKs by something which is at even smaller temperature, all of these ratios will become bigger in magnitude, but because of the negative sign for all of them, once again this sum will become even smaller. So, replacing all the Tj's here by T plus and all the Tks here by T minus will make this smaller than or equal to this one, which already is smaller than or equal to 0. So this whole thing is less than or equal to 0. Now here, the T plus is the same for each and every term in the sum. So is the T minus here. So we can take the T plus out of this sum and T minus out of this one. If I take T plus out of this sum, you are left with sum of all the Qj's which are positive, which of course is what we have called Q plus earlier. So this side is Q plus by T plus and this is simply Q minus by T minus. So what we end up with is this ratio Q plus by T plus Q minus by T minus has to be less than or equal to 0. Now the rest of the work is exactly the same as the one we did for the Carnot theorem. Q minus is W minus Q plus, simply because Q plus plus Q minus, the net heat taken in, must be equal to W for any cyclic process. And just rearranging that will tell you that W by Q plus, the efficiency of the engine, has to be less than or equal to 1 minus T minus by T plus, which of course is the efficiency of the Carnot cycle running between the highest and the lowest temperatures. So a general heat engine cannot be more efficient than a Carnot cycle running between the highest and the lowest temperature attained during the cycle. This is the generalized Carnot theorem. Indeed, if we go back a bit and try to figure out when will W by Q plus, the efficiency, be equal to the maximum value, for that to happen, of course, you have to have two things. First of all, this less than equal to should become an equal to, which of course is possible only if the cycle is reversible. So for this to happen, the cycle has to be reversible. But this alone is not enough. This statement has to reduce to an equality. Now here, you have a bunch of heats taken in, positive heats, which are dividing by the corresponding temperatures, and you have replaced that here by the largest of the T pluses. This will always reduce the quantity, so this will become a less than, unless there is only one temperature at which heat is taken in. So the sum does not have multiple terms, has only one term at temperature T plus. And by the same token, this will also become a reduction, replacing the denominator by a smaller number but with a negative ratio overall. This will always be a reduction unless all the QKs are 0 except for the one at temperature T minus. In other words, in order to actually exactly attain W by Q plus equal to 1 minus T minus by T plus, the maximum possible efficiency, our cycle must be a reversible one, which takes heat only at temperature T plus and rejects heat only at temperature T minus. So, not only is the efficiency of the cycle bounded above by the Carnot cycle efficiency running between the extremal temperatures, the extremal efficiency is obtained only for this Carnot cycle. For anything else, you will have a smaller efficiency. This is the generalized Carnot theorem. Now, by this time, you should be convinced that the Clausius inequality is a very, very useful result. And the fact that it's exactly equivalent to the second law really makes it obvious why it's so important. However, it may come as a bit of a surprise that this inequality is hardly ever used in this form in thermodynamics, for the simple reason that it's used more as a stepping stone towards a much more useful concept, the concept of entropy. So let me indicate how that concept comes about. In the rest of today's lecture, we will discuss entropy and its consequences in much more detail in later lectures. But notice that the Clausius inequality especially for reversible cycles, tells us that in a closed loop, an integral of d cross q reversible over t gives you 0, and that immediately tells us something, that if you were to integrate d cross q reversible by t from I to f, where I is some equilibrium state of the system and f is some final equilibrium state of the system, then this integral is independent of the path taken to go from I to f. The reason behind that is simple. If you consider two such paths taken by the system to go from I to f, indicated here by the blue line and the green line together, we can always see that the integral of d cross q by t along this blue path minus the integral along the green path, which is nothing but the integral from I to f, added to the integral done along the green path but from f to I, this must be 0, because these two paths taken together with the green path being traversed in the other direction gives you a closed loop. And Clausius inequality has told us that for a reversible cycle for which this becomes an equality, this sum must be 0. So the integral along the blue line and the integral in the same direction from I to f along the green line must be equal to each other. Now that tells you that here we have a quantity whose integral is path independent. Of course, this means that although d cross q is not an exact differential, remember that is why we wrote it as d cross q and not dq. There is no function q whose differential gives you d cross q. Neither is d cross q reversible, but d cross q reversible by t is an exact differential. Differential of a function of the state and the state alone. This is the function which is called the entropy, and we are going to talk a lot more about this in the next lecture. Let me just point out one thing. What the Clausius inequality really tells us is that although d cross q under reversible conditions is not an exact differential, it does have an integrating factor. There is a function of the state variables which can multiply this differential by, after which, that is after the multiplication, the differential becomes an exact one. This integrating factor, of course, is nothing but 1 over the temperature. So the reason why the quantity called entropy exists is that this differential, the infinitesimal amount of heat absorbed during a reversible process, although not an exact differential, can be made into an exact differential by multiplication by an integrating factor. That's a very non-trivial mathematical property for this particular imperfect differential. And it is the second law in the form of Clausius inequality, which becomes an equality, remember, for a reversible process, that leads to this very important restriction. We will meet the entropy in a big way in the subsequent lecture, and we'll go on to use it in many different applications in the rest of the lectures. But this is a very important point which has to be borne in mind. The fact that the differential amount of heat absorbed under reversible conditions has an integrating factor is a non-trivial fact about the physical world, and this non-trivial fact is basically at the heart of the second law of thermodynamics. More on this in the next lecture. Bye for now.